That's right. Yes. Yes. All right. So, okay. So I'll be talking about acoustic oscillations. In particular, we're discussing a couple years old now way of doing perturbation theory for a large-scale structure. And so this is in a couple of papers, a recent paper which applies this to acoustic oscillations. And at the end, I'll probably mention briefly extension of this to higher order statistics. So most of what I'll be saying is going to be about the power spectrum of densities, of the density field. All right. So when you are looking at the large-scale structure at low redshift, you have to deal with nonlinearities, because even at large scales, the density field is weakly nonlinear. And so you start, the usual approach is because the universe becomes homogeneous at very large scales, and fluctuations are therefore small, you can expand in the amplitude of density perturbations. And that's what I will call the standard way of doing perturbation theory. And this is something you're probably all familiar with. So if you're doing two-point statistics, linear perturbations is leading order for doing two-point statistics. As you look at higher and higher order statistics, the three-point function or the bispectrum, you need second order, four-point function or time spectrum, you need third order, and so on. And so at large scales, this kind of perturbation theory approach gives you the leading order contribution to all the statistics. And instead of having to tailor the name of the order for a given statistic, you can turn into a diagrammatic language, which I will use briefly. I won't use too much in this talk, only to explain some things. But all these things can be said to be just a tree-level perturbation theory, where the diagrams that you draw for these statistics are all tree diagrams without any loops. So this will become more clear in a few slides. And so we summarize this by saying that tree-level perturbation theory gives a asymptotic behavior at very large scales for all the statistics, no matter what you are calculating. So immediately, because in large-scale structure, surveys start local and they become bigger and bigger, unlike the CMB, where we start with the full sky and we go lower and lower, higher and higher resolution to smaller scales, right? So, unless we wait long enough until we can probe very, very large volumes, they also always have to deal with nonlinearities, and small scales are included in your problem. So immediately you have to ask the question, what are the nonlinear corrections to these leading contributions? How important are they? And once you start dealing with perturbations which approach size of order 1, then you can immediately convince yourself that as you start, say, let's do the power spectrum, which is the easiest thing, right? So if you write the power spectrum, and this is your initial, say, from the CMB power spectrum, so linear theory gives you just an independent growth factor times this, and then so this will be the tree level that I was talking about before, and then you start including nonlinear corrections. And so the size of these guys compared to the leading order, so if you do the ratio of this to this, it will just be the amplitude of density perturbations, which will be just, because we are in 3 dimensions, is k cubed times p of k. Okay? So when this parameter becomes of order 1, then this term becomes of order p linear, this one becomes of order p linear, everybody becomes of the same order. You are not allowed to truncate this expansion at any finite number. So you have to resum all the terms here. Okay? And this is going to be the strategy that I'm going to follow. I'm going to try to do some resummations and show that you can actually build out of this ill-behaved perturbation theory, when you approach size of perturbations of order 1, you can build a well-behaved perturbation theory, which will have a completely different behavior. Okay? So let's see how this works. Okay? So this is the so-called renormalized perturbation theory. And so the strategy...
So why do you need resummation?
Summing. diagrams, like all the contributions. It's in the very... why you need it. Oh, I thought you said why you mean it. What do you mean by? Well, you need it because otherwise it doesn't work. You cannot prove non-linear scales.
So you will talk about large scale.
Yeah, no, but as you'll see, there are important corrections at scales of order 100 megaparsecs that you actually get wrong if you don't do this. So an example of that is the variant acoustic oscillations, which I'll discuss.
I have my own answer. I just wondering.
Yeah. So yeah, this is really needed. There are some. So you will see. I'll show the difference between doing standard perturbation theory and this type of perturbation theory. So the strategy is you. Sorry, so you try to. That strategy will be to convert this standard way of doing perturbation theory into something which is more useful. As a result, we are going to end up with a different type of perturbation theory, but the expansion parameter is not going to be the amplitude of density perturbations. Okay, so that's the first lesson of this approach: is that it's not going to be there's not going to be a parameter which becomes of order unity, and then you are in trouble. Okay, so it's not going to be the amplitude of fluctuations in which we will be expanding. An important property is that once you do this kind of thing, you'll see that the large scales are effectively shielded from the small scales where things are highly nonlinear. And so you can actually truncate, differently from the standard approach, you can actually truncate this expansion to certain order, and the terms that we are throwing away, they only become important at very small scales. So if you are looking at large scales, then you're fine. Okay, so that's going to be the strategy. And the basic trick, if you wish, or result that's going to come out is that if you essentially what we're going to be doing is we're going to do this kind of resummation of nonlinearities in such a way that the growth factor, which is in linear theory is just a function of redshift, a function of time, becomes something else, which is a function of time and scale. So let me explain what I'm doing here. So you can always write the growth factor as the cross correlation between the initial perturbations and the final perturbations at the redshift you are looking at evolve in linear theory, and then divide by this normalization. Okay? So if linear theory holds, this guy is just d0 times d plus, so this is correct. So what we will see is that when we resum an infinite number of diagrams that are coming from solving the equations of motion, we see that this quantity gets renormalized, and the renormalization that we are talking about is just equivalent to replacing this linearly evolved density perturbation to a fully nonlinearly evolved density perturbation. Okay? So this is going to be the result, which I'm going to get into a second. And now you see that this guy has a very different behavior than this one here. So when you go to low k, so you look at very large scales, right? So then perturbations evolve linearly. So this guy should become this, and that's what happens. However, when you go to very small scales, so if you take the limit where k goes to infinity, the cross correlation between the non-linearly evolved density field and the initial fluctuations should be driven to 0, right? Because you start with some density perturbations in the early universe, you evolve them non-linearly, they'll collapse and so on. So they get very, very modified at small scales. So when you do the cross correlation at a given scale, at a fixed k between the final condition and the initial condition, then that cross correlation is driven to 0. And so this guy is actually going to go to a constant independent of k at large scales, and it's going to be driven to 0 at very high k. And this is a property that is impossible to capture at any finite order in perturbation theory. So this is the resummation is going to give us this property, which is crucial for what's going to come out later. So I'm going to explain this in more detail in a second.
So a stable clustering, like, give you that, or?
No. Yeah, so stable clustering is a statement about what are the what the pairwise velocities are doing at small scales. So you can translate this into something like a power spectrum, but this is a different quantity. So this is a cross correlation between the nonlinear density field and the initial perturbation. So any nonlinearly evolved field will have this property.
It basically means loss of phases.
Yeah, you lose memory of the initial conditions, essentially. So if a given high K mode, right, the high K mode, you start with some amplitude there. You let it evolve, it grows, right? And then things collapse at small scales. They get very modified. So the high frequencies get very, very modified.
It's like turbulence at small scale.
Yeah, so essentially you cross-correlate and you get zero between what you have.
These aren't randomized, though, right?
Well, not exactly, because it's very non-Gaussian. So they have some. They,
Loss of KPIs means that if you take the full ensemble, the phases between small scales and different halos, they randomized. What you mean is you can concrete halo, it builds up from modes around the peak. But if you take average over ensemble, it means different points of no different halos, no correlation.
well, I'm not sure that means random, because to form a halo, right, it's a very coherent thing
Different modes.
in different places.
That's right. It's constrained realization will be highly correlated, but average over ensemble will be completely like phases.
Okay.
These peaks occur at the places where the long wavelength modes also have peaks.
This is strong correlation. This is constrained realization.
Yeah, there is some correlation, but as you
Constrained realization.
first there is motion. These big halos actually move quite a bit. So if you look at peaks in the final density field, they are not at the same places as in the initial density field.
Because although this should mean gets most of that. So.
You get some of that.
Really sub-halo scales. It's not on the scale of the typical halo.
This has nothing to do with halos. These are much larger scales.
But the scale where the K goes to infinity.
Yes.
We're talking about a K that's not the K where galaxy-sized halos are clustered with.
No. We'll get to that.
Smaller than that.
No, it's much larger. So it's like of order 10 megaparsecs, roughly. I will calculate exactly what this limit means, okay? So there will be K much larger than the RMS velocity fluctuation. So we'll get there in a second. Okay. So now I need to explain how we actually, so that what I'm claiming here is that we can calculate this quantity, at least in some, which I would call a reasonable approximation. We can calculate this in the fully nonlinear theory in some sense. Okay, so I wanna, explaining this will take a long time. So I'm gonna try to motivate exactly how we can calculate this object. Okay, and for that I need to use a little bit of the diagrams. So for a few transparencies, I'll try to motivate, sketch how we are able to calculate something to all orders in perturbation theory. Okay, so this is this resummation thing, and so I'm gonna write the standard way of doing perturbation theory here, which is, so you start with initial conditions. So this blob means initial perturbation. Okay, and the perturbation could be density or velocities. So this phi is a vector whose first component is density, second component is velocities. Okay. So this is linear theory. You start with some initial condition, and you propagate forward in time until time eta. Okay? And eta is the log of the scale factor, or the log of the growth factor. So this little arrow here means propagation forward in time. Okay? And it's described by the linear propagator, which is just the thing you are used to in linear perturbation theory. So there is a term which is the growing mode. Okay? So e to the eta is the growth factor, so it goes as the growth factor, and then there is a decay mode, which goes as growth factor to the -3/2. Okay, so it's essentially, so you see there are two modes in a self-gravitating fluid in cosmology. There are two modes. One in which if you set densities and velocities proportional to each other, then perturbations grow. Physically, that means if you have a density peak, you should set velocities pointing towards the high of the peak, so later it evolves. If you set it in the wrong way, you set the velocities pointing away from the peak, then you excite the decay mode. Okay? And this is going to become important because although when perturbations evolve linearly, after a long time, these guys are gone. But once you start building interactions, once you essentially have a mode interacted with another, after interactions, part of it is going to go into decay mode and part is going to be into the growing mode. So you have to take into account, once you have nonlinearities, actually this structure becomes also important. Okay?
This is a way to rewrite hydrodynamical equations with some gravity. Right? The Poisson equation and
yeah, so we are solving here three equations: conservation of mass, conservation of momentum, and the Poisson equation.
and it's a single stream.
Yeah, in the single stream. I will say something about multi-streaming at the very end.
It's nothing but the field equations.
It's nothing but?
Fields equations.
Yes.
Variables, potential and
Yes.
velocity potential.
Yes. Yes. So here, so this vertices here denote interaction. So here we have first order perturbation theory. Okay, we start with this and an initial condition, and it propagates forward in time linearly according to this thing. Then we have second order, which is two perturbations interact at some intermediate time. So they propagate forward linearly without interactions. At this time they interact and then they propagate forward again. And here is where after interactions, part of the result is going to be in the growing mode and part in the decay mode. So you have to take into account this. And the same thing. So this is third order. Okay, so you have three guys interacting to construct your perturbation at time eta. Fourth order, you have these two things, and so on. Okay, so you are building in the usual way. So this is the representation of the density field at time n, at time eta. And so if you calculate the power spectrum, you calculate the 2-point function. So essentially, you take this guy, you take another one of these, and you take the average of one of these things against a similar one. That's the 2-point function. And then you construct these kind of diagrams. Okay. So these dashed lines is where these two trees, right? This is like each of these diagrams is a tree, right? So I'm doing the 2-point function, so I have two of these. When I do the expectation value, I just glue the two things together where the initial conditions are. So this is the dashed lines is where I glue the two things together. Okay, so this is the first term. So it's an initial power spectrum now, propagated forward in time. Okay, for each of the legs. So this is the initial power spectrum, and this is the final right here. So this is linear theory. So you see it's a tree diagram without loops. If you keep doing that, then this is second order against second order, right? So you get a one-loop diagram. And then you have something more complicated. These three diagrams are all one loop. And then if you keep doing, there are two-loop diagrams and so on. So time is now tricky because it's a power spectrum, right? So I have two fields. So time is going from this dashed line forward in this way and forward in that way. Okay? Because I took two of these things I had in the previous page and I put them together, right? And an average. Okay? So you see where I glue the two things are these dashed lines. So you can see where I've been gluing things together. Okay? So it takes a long time so I'm not trying to claiming that just by looking at this in 2 seconds you will. But
So the blue depth seems to have a funny time arrow as well. So lead number 8, for instance, right? So
this one?
the left loop, basically.
Yeah.
On the number 8 left loop. The time
This and this are the same, essentially. Say that again?
Yeah, for the second loop there, the time sort of starts in this plot there.
Right. So this time is later than this one. There are constraints, right? So times is going from this forward, is going to the left here and to the right there. So this time is before this one.
Then you go back in time?
No. You go forward in time like this. You start at time 0 from the crosses.
Time be important for diagrams.
Time is very important. The reason why we can do the resummations is because we have broken this into, so you will see in a second. Time is important for this.
Because in field theory, you deal with momenta. And reversing errors.
Well, but you don't have initial conditions, right? This is a different problem, right? So this is an initial boundary problem. Yes, initial value
You
problem.
need to keep those errors to know how initial conditions fit there in the diagram.
Yes, yes. Right. So time propagates in the sense of the arrows. Okay. Okay.
You will confuse it there. How we keep those.
Right. Well, this guy is 0 if this time happens later than this one. So So this guy here is a retarded propagator. So if eta is less than 0, it's actually 0.
So at the end of the day, you need integral, right? And this is just a rule what you substitute in the integral.
Yeah. These are the Feynman diagrams for this theory. Yeah. So okay. So this guy is just the growth factor. Okay. So this is linear theory. The initial power spectrum times the growth factor square. Okay. So that's my red circle. But now if you look closely at all these diagrams, you see that there are a whole bunch of diagrams that act the same way as the growth factor, meaning that I start with the initial power, and if I just replace this blob by an arrow, right? Because you see there's an arrow entering and an arrow exiting, it behaves the same as this guy. Okay? This term also in the other leg. This term also, I have something here, and then you can replace the whole circle by an arrow. So these guys are actually what I said before, that the growth factor gets renormalized. So you can think of these guys like a nonlinear contribution to the behavior of this propagation forward in time. So if you do that, you construct the diagrams for the propagator. So this is the linear propagator that I said before. This is the one loop diagram for the propagator, and you can construct all the loop diagrams. So this is the only one loop diagram, and then these are all the two loop diagrams. Okay. So how am I going to resume this in the full nonlinear theory? It would be nice if I could sum fully all these diagrams, okay? But that's not, unfortunately, that's not, or at least we haven't been able to do it. But what we have been able to do is to sum the most important contributions to it, okay? So here comes the key element of why we are able to do these resummations. So, and we are able to do this resummation in a limit where the momentum where k, the frequency you are looking at, is large, and large compared to what is going to come in a couple of slides. So if you look carefully at what's going on here, you notice that if this momentum is large, right, meaning large compared to the other momentas here, okay, so in this case there is a one loop diagram, so there is only one extra momentum. So there is a particular direction in the diagram where the large momentum is flowing. So in this case will be this line here. In this case will be this line, right? These are all momenta that I'm going to assume to be smaller than the external momentum where I'm calculating things at. Okay, so I'm integrating over all these other q momenta. And so remember, the physical interpretation of this object is the cross correlation between initial density perturbations and final density perturbations. Okay? So, and as I said, this cross correlation is going to be driven to 0. So if I want to calculate this, a good approximation to that, all I have to resum are the diagrams that cross-correlate the most with the initial conditions. Okay, because those are going to be the ones that give the leading decay of the propagator. So I just have to find within all this infinite number of diagrams who are the diagrams that cross-correlate with initial conditions the most, and those give the leading contribution to this. So you see that to two loops there are many diagrams, right? But they can be organized according to how many times they interact along the line of highest momentum. Okay? So for example, this one has a large k flowing this way, and there are 4 interactions along that line. This one also has 4 interactions about that line. But for example, this one has only 1, right? If k is high, it flows like that, right? And there's only here 1 interaction. that is directly connected to the initial conditions. Okay, so here's where the time dependence comes in. Okay, so remember what happens. So when perturbations grow away from initial conditions, they are in the growing mode, right? So this interaction is going to happen with this guy in the growing mode. However, this one comes after interactions which do not come right away from the initial conditions. So there's going to be an interaction here, and after that, it's going to be some decaying mode until I get here. And so this one is going to cross-correlate less with initial conditions because of that. So we can organize all the diagrams according to how many times they interact along this line. And so we can resum to every loop. We can keep only the terms that have the most cross-correlation with initial conditions. And those are the ones that have the largest number of interactions. So the 2 loops will be 4 interactions. And so those kind of diagrams, subset of, it's an infinite number of diagrams, but it's a subset of all of them, can be generated by this kind of diagrams where, so this is the one that I said, this is the 1 loop diagram, this is the one that's going to become the 2 loop diagram that generates all the 2 loops that have 4 interactions. So they are very simple. So essentially, they are very simple in terms of the initial conditions. So if you're looking here at final time, and this is your initial condition, this is the high momentum. They're all coming from with the growing mode, interacting, and you can show that in the high K limit, this still keeps in the growing mode. This is in the growing mode again, interacts, is still in the growing mode, So all the time is in the growing mode, so it cross-correlates the most. So these are the dominant contributions.
Looking at rescattering in a sense, least rescattering even more. Even more is moving and you're looking what disturbs, what rescattering.
Right, essentially what you're doing is, from this point of view, is like the small scale modes act like there is like a random walk to the motion of the
Motion of particles through the media.
Right. So it's like the motion of the as you get clustering, this motion can be interpreted from the point of view of the large scale mode as a diffusion, a random walk, and that's why you get a Gaussian at the end. You'll see. So the amazing thing is that when you include all this infinite number of diagrams, infinite subset, you can resum it exactly in the high K limit. And the answer looks like this. And here is where the scale appears. So you were asking before, what's the scale? What do you mean by K going to infinity? So there is a scale that appears, which is the amplitude of velocity fluctuations. So this is the initial power spectrum divided by K square. So this is density power spectrum. So divided by K square is the velocity. And so if you are in the regime where K is much larger than inverse RMS of the velocity field, then you can show that all this resummation gives you this simple answer.
It's like a Wiener process, right?
I don't know. What do you mean?
You expect this type of broadening to Gaussian.
Yeah, maybe. So you see, this has the properties that I said before. If you look at low K, right, this exponential goes to 1, you recover the growth factor. As K goes to infinity, then this is driven to 0. Okay. And so if you do this calculation at finite order in perturbation theory, it will be equivalent to expanding this exponential. So depending how many terms you keep, instead of going to 0, you will either go to plus infinity or minus infinity, right? If you expand this in series, right, you get a K square, a K to the 4th, and some come with negative signs, some with positive. Depending on to what order you truncate, you either go up, you go to plus infinity or minus infinity. You never get to 0, which is the physical answer. So that's why standard perturbation theory breaks down, because it doesn't see this. So this scale is actually pretty large. So if you calculate in Fourier in K's, so it will be inverse this is of order 0.15 at redshift 0, which is essentially 6 to, depending if you put the pi's or not, between 6 and 20 megaparsecs at low redshift.
All I meant was, for K to be much larger than that, it has to be much larger than that number. It has to be larger than the typical scale that's collapsing.
Right, but this is quite big. It's not a halo. Yeah.
The scale where it becomes a appreciable effect is very big, and then one where it's at order 50% is relative to what people might have guessed before, but the scale where it really goes to zero is in the pretty strongly nonlinear regime, where you shouldn't think of the structure you're seeing as the clustering of the modulation of halo clustering as much as being within the one halo term.
Okay, we'll get to the comparison with halos in a second.
So for k of 1, for example, it's a 0 basically.
Yeah, right.
And, k of 1 is some sort of galaxy scale.
It's power is dominant rather than
Right. Well, let me get to the halos in a second. So we'll see, because this damping is relatively large scales. If you are looking at something like baryon acoustic oscillations, it has this property that once you include this effect, it shields you from what's going on at very small scales. So this is a nice property. It will become more obvious as we go along. So how does it work compared to embodied simulations? So here I have, again, the propagator now divided by the growth factor, so it should go to 1 at very low k. And this is for density perturbations, this is for velocities. And this is the prediction is the solid line, and the squares are the embodied simulations. And this is at 3 different redshifts. Okay, so this is redshift 5. So as you move into lower and lower redshift, these nonlinearities kick in at larger and larger scales. So you drive this to 0 sooner. Okay? And so this resummation works really, really well. So let's now, the goal is not looking at this cross correlation, but the goal is to model the power spectrum. Okay? So this was just the resummation we were able to do, and now let's see how it impacts the power spectrum. So what you can show is that, so this is the standard way of writing the power spectrum that I wrote before. So this is linear theory. This is the one loop corrections, 2 loops, and so on. So what we are able to do is to reorganize this thing into something that looks like this. Okay? So we have 2 terms. So each of these terms contributed to this G. Okay? Infinite number of terms contributed to this G. And then also these guys also contribute to the second term. So what is this breakdown here into 2 terms? Well, the first term here is the contribution to the nonlinear power that is directly proportional to the power that you have initially in your density perturbations. Okay? So this is just a modulation or damping of the initial power at that k. So if you have a power spectrum which is non-zero, and then suddenly it drops to 0, right? This term will not create power at higher frequencies than you had at the beginning. Okay? So this is a very physical description. So it tells you how much of the initial power is related to the power that you had at that particular scale. And this thing is what we call the mode coupling power spectrum, which generates from interactions of modes, can generate power at higher k's than you had initially. Okay? And so this guy we had resummated to all orders, but this one, what remains is a perturbation theory for this quantity now. Okay, it would be nice to also resummate this, but we haven't been able to do that yet. But what I claim is that the perturbation theory that results in this quantity here is very well behaved, and you will see in a second exactly what I mean. Okay, so if you write the power spectrum like this, you can write the correlation function in a similar way. So it's just Fourier transform. So this multiplication becomes a convolution, and then this guy, the Fourier transform of that we call the 2-point function, the mode coupling 2-point function. So if you have here some features, like in baryon acoustic oscillations, psi 0 has a peak at the sound horizon at recombination. This G is a Gaussian, so its Fourier transform will be Gaussian. So this term will actually convolve the initial 2-point function that has a peak at the acoustic scale with a Gaussian kernel, so it will broaden the feature. And this, as we'll see, this will shift the feature towards smaller scales. So let me now show some results. So this is just a pictorial, well, it's a representation of what I wrote before. So you start with a linear spectrum, which is here, the solid line in black. Okay, you see the baryon acoustic oscillations in the dark matter get imprinted. Okay, and then the nonlinear power spectrum, which is this blue line, is the sum of two contributions. One which is g squared p0. Okay, so you dump the linear spectrum with this Gaussian, and then you add this power at small scales. Okay, so this is the power that gets generated out of interactions, the mode coupling power spectrum. So if you now Fourier transform and look in the correlation function, the linear correlation function has this peak, this broad peak at the acoustic scale. So this is the sound horizon at recombination, about 100 megaparsecs. And this is essentially coming from the same acoustic peaks you see in the CMB. It's the same physics. So only that in Fourier space, it's a series of peaks. When you Fourier transform, it's just a single peak in the correlation function. And so when you convolve this linear theory with this propagator, it gives you this red line here. So it broadens the peak. Okay? And if you look at what the effect of the mode coupling correlation function is positive towards the left of the peak and negative toward the right of the peak. So it gives a correction whose net effect is to add here and subtract here, so it will shift the peak towards smaller scales. Okay, so now let's compare the standard expansion with the new expansion. Okay, so this is the old expansion when you expand in the amplitude of fluctuations. So you start with some linear spectrum. So now this one doesn't have wiggles. It's just to show an example. Okay, so this is the linear spectrum. This is the one-loop correction. This is the two-loop correction. Okay, so you notice here, so this is negative. So dashed lines is negative. Then it turns positive. This one is positive. Then it turns negative. And so if you look at very large scales, this expansion converges, right? Because you are adding large thing to a smaller to an even smaller. So it's well behaved. But you see, as you probe the nonlinear regime, all these different contributions are of the same order and different signs. So there is a lot of cancellation and a lot of, and that's how perturbation theory breaks down. And essentially, it's because we are expanding this propagator to fixed order. So you have some large negative and positive contributions. And so in the new expansion, every term is positive and is well behaved. It only dominates in a narrow range of scales. So in the new expansion now, you have the leading order is just g squared times the linear spectrum, so it dumps it down. And then this mode coupling is a series of bumps that as you increase the order, they dominate at smaller and smaller scales. Okay? So if you want to calculate the power spectrum up to this scale, then you just need a few terms, because all the terms that continue here, they are just very, very suppressed at the scales you are looking at. And so you can forget about those. So the property of the perturbation theory that results is completely different.
So it looks by eye that it's converging very slowly once you get to those mini.
Yes. So this is an example. I'm skipping some things here. Huh? Yeah, it's a schematic. Schematic means that I'm doing this instead of doing it in the exact dynamics, I'm doing it in the Seldovich approximation, where it's much easier to calculate all these things. So in the Seldovich approximation, these guys actually pile up quite a bit, and eventually you need a lot of them to calculate. In the exact dynamics, they are farther spaced, and you can see also from here that the nonlinear power spectrum is always smaller than linear, which is not something that happens in reality. So this is because I'm using the Seldovich approximation to illustrate this.
Maybe part of the reason they pile up is just that's the correct answer. That sort of
Yeah. So, well, yes. In this case, is the correct answer. You can check that if you sum all these guys, you do get the right answer that you can calculate without any approximation. So in the Seldovich case, this guy can be calculated without any expansion whatsoever. Huh?
what I said didn't make sense.
Now, if you compare with the Halo model now, this looks, for those of you that know the Halo model, this looks similar to the Halo model. So the Halo model, there is a when you put dark matter into halos, there is a so-called two-halo term where particles are in different halos, right? And that will be this one. And in the halo model, this is suppressed by the halo profile, so it's also damped, but not damped in this particular way. And then the one halo term in which pairs of particles lives in the same dark matter halo. And if you break that into contributions of different halo masses, it will look like something like this also. So as you sum over the mass function, you will get all these contributions. However, there are some very important differences with the halo model. So now let's go back to no schematic, but the real thing. Let me now calculate exactly what these terms look like for a power spectrum with baryon acoustic oscillations and so on. So now I'm calculating the mode coupling power. Okay, I already compared the first term, the propagator, with simulations. Now I want to compare the calculation of the mode coupling power. Okay, so roughly speaking, you see at large scales the power spectrum is of order 100 in these units. So now we are looking at these guys, which are much smaller. Okay, so the next you can see here I'll go even up to only up to 10 or so. So at large scales the linear spectrum is right there. Okay, so you can do this in the simulation as well. You can measure the power spectrum in the simulation. You can measure the propagator. This is the initial power spectrum. So you can measure this in the simulation. And these are the measurements in the simulation of this quantity with error bars included. And this is the calculation of the mode coupling power to one loop and to two loops. And so you have to keep calculating. So otherwise, eventually, you don't get the right answer. Okay. So I only calculated up to two loops because that's enough to look at baryon acoustic oscillations, which are in this region here. So as you see, it works really. It works pretty well. And if you compare now again to the halo model, if you follow this analogy that these guys are like in the halo model summing over different halo masses of the one halo term, you actually get something very different. You get just a constant at these scales. Okay, eventually you get something that does like that, but at these scales, looks like this. Huh? So the halo model is you assume that all dark matter, once you evolve nonlinearly, lives inside dark matter halos. Okay, so it's a very drastic model. So essentially, you say everything collapses into halos, and in between halos there is nothing. It's just all empty. Okay, and because you know the mass function of these halos, how many halos are of a given mass. Okay, and you know how these halos are correlated. If you assume linear theory, which is what people usually do, then you can calculate all the correlation functions. And so if you are doing the two-point function, there are two possibilities, that the two particles are in different halos, and that's the two-halo term, and then two particles at small scales, two particles will be most likely inside a single halo, and that's the one-halo term. And in that,
it's not dynamic. It's just
no, it's not dynamic. It's a prescription. And you see that the halo model doesn't predict this very well at all. And again, this is another signature that this physics has nothing to do with the physics of virialization. It's something that happens outside halos. And so one should be careful when some people sometimes like to use a halo model, mostly because it's easy, and partly because you can fit most of these ingredients to simulations. You have to be aware that it's not just linear theory outside halos and then virialized halos. There's a lot of stuff in between. Another way of saying this, if you look at the density field, it's not that the density field is either linear or is inside virialized regions of mean density 200. There is a lot of range between densities much smaller, perturbations much smaller than 1 and 200, which is all the filaments and all this complicated stuff, which lives at large scales. And that's what is being described by these terms here. Okay, so now I'll try to give you the results for the power spectrum and how acoustic oscillations evolve due to nonlinearities. So the motivation here is that these acoustic oscillations essentially have imprinted a scale, which is the distance the sun can travel when the universe recombines. And you can use that scale as a ruler by looking at the sky and measuring that scale, because that scale depends on simple physics, like how much baryons you have in the universe. You can calculate that scale, the physical scale. You can measure at an angle, and from that you can get constraints on geometry. So you can use this as a probe of expansion history. From here you can constrain dark energy or modified gravity as an explanation of the acceleration of the universe. However, this scale gets modified by nonlinearities, and the goal is to figure out how much they are modified if you want to use this in precision surveys. And the challenge is that 1% error in the sun horizon, which is roughly the scale that you can define from the positions of these wiggles in the power spectrum, induces about 5 times larger error on the equation of state of the dark energy. So if you want to measure, the goal, as you may have heard, is to measure this down to a percent level. Then you need to figure out this scale to sub-percent. So we are talking about very challenging experiments. And although this is at 100 megaparsecs and nonlinearities are weak, we are trying to measure this to say 0.2% or something like that. So you have to really look at this in detail. Okay, so here is now a detailed comparison of our calculations with simulations. So to show these wiggles in the power spectrum, I divided by something that is a smooth power, so you can see the wiggles now much better. Okay, and you notice these wiggles are very small amplitude. Okay, so they are modulating the power spectrum, say, by 4% up and 6% down or so. Okay, so it's like at most 10% contrast in power. And so this is a redshift 0, and these are the results of measurements in n-body simulations as a function of k. And so here are all the ingredients that enter into my calculation. The first one is the first term, which is the damping times the initial power. So you see linear theory gets damped quite a bit, right? And so then you include the first term in mode coupling. You get this line here. So it explains this first oscillation, and then it goes away, and then you include the next term, and it gives you the red line. So you see the red line is describing the simulations pretty well. And if you just use linear theory, you will get the dashed line here. Okay? And if you do the same at redshift 1, there's a similar. There the nonlinearities are weaker, but still they are important. So we do see some differences between our prediction and the simulations, but they are below percent or so. And our calculation, we don't think is accurate to 1%. There are some effects which we are approximating, and we are now trying to do a bit better. But
how many loops are you include in calculation?
2 loops. So this is up to 1 loop, and this is up to 2 loops.
How about third loop? Maybe
Yeah, the third loop will kick in here. At this scale, roughly, we cut it where we cut the axis where it will kick in. And it will actually, if anything, because it's positive, it will add more. So it will create more difference here. But that's where other approximations that other renormalizations that we are not doing enter. And that's what we are working on right now.
But
So,
how about just a simulation? I mean, which precision?
yeah, we don't know.
Well, you can make some tests, right?
Yeah, you can. People have done conversion tests, but for smaller scales. And typically, there are different kinds of tests you can do. For example, doing the same numerical code with different resolution, that tends to give less than percent differences. But if you do different codes, then the percentages difference go up to 3%. And depending on what you look at, sometimes even 10% at small scales. But at these kind of scales, I'm not aware of a comparison that, because you see, we are here getting error bars which are of order 0.2% in the simulation, right? But to do that, you need to run, 50 realizations of gigaparsec volumes. So it's really painful. So it hasn't been done.
Which simulation?
This is using the Gadget 2 code written by Volker Springel. Yeah, so
Well, then who made the simulations?
well, I run the simulations, but the code is public.
How do you then, for instance, determine the force accuracy? There are a couple of parameters engaged that.
Oh yeah, there are many. So yeah, there are like 8 parameters. So we have tested. So essentially, these are simulations that run from Redshift from Redshift 49 to 0 in about 2,000 steps. But we have also run other realizations which have much more stringent force integration, accuracy, and.
Did you try to vary the initial redshift?
Okay, so we have tried. So in fact, the way the initial conditions are generated here is using second-order perturbation theory to generate the initial conditions, and we think that's important, particularly once you start looking at these kind of scales, because people usually start their simulations using Zaldovich, which is linear theory, which is not accurate enough. So if you change the initial redshift for this type of initialization of the simulations, there is no change whatsoever. You can even start the simulation at redshift 15, which is crazy, but we went as far as to start it at redshift 11.
Earlier as well. You started earlier as well than 15?
We tried 99, and we tried 250. So, but it doesn't make any difference.
This is a world expert on starting redshift of these.
Yeah. So now people are. We have actually. I should advertise. We have a public code which generates initial conditions for simulations, and so you can download it from my webpage. Other people now. I was talking to Volker last week. He has now a super duper mega hyper adaptive mesh, whatever. So it's incredible. So they are doing this very, very nice work on. I'm not a simulator. I basically did what you can do in a few days, but these guys are now, they are pros. So they are doing like really well, and they are finding the same results. Although for the mass function they haven't yet tested, but they are in the process of doing that. So if you want accuracy of order % or so at low redshift, you should be careful of how you initiate the embodied simulation. Yes. Yeah, by now there are 5 or 6 different methods which have similar ideas. So one is Pat's method. Who? I haven't seen that one. So there is a Mataresi and Pietroni where they do renormalization group kind of approach. And there are a couple of Japanese groups that have done similar things. There was a paper by Matsubara last week or 10 days ago. Well, I think it's fair to say that nobody has compared it to simulations to this accuracy. So.
If you put those results, this plot,
I would say comfortably mine would not. Mine would take a lot of work to get to this point.
because
Right.
next
Well, we are in.
It's different enough that that's not really the correct comparison. His is just a lot better.
Matarese also has, at least I wouldn't say issues, but there are some things I don't quite understand. So basically what they do is they convert the nonlinear evolution into a rate equation. And so basically you do essentially the time derivative of the thing you are calculating, and there is a rate. And that rate is put only to one loop. So the way to generate 2 loops and higher loops is by concatenating one loop diagrams as you time evolve. And as I showed before, there are many, many diagrams that cannot be built in that way. So for example, this gets a bit technical, but since you ask. For example, this diagram can be calculated as you evolve in time, concatenating this guy with the next guy. But how about this one, right? If you're between one time step and the next, your time lands here, you will not be able to account for this or for this. So it's at least, maybe it's just I don't understand their calculation well enough to say, but it's not clear to me how they. What?
I thought they get the same result as
Well, I don't know. How do you know?
Isn't that what they say?
Yeah, that's what they say, but I'm not sure, because one thing I would like to see is their propagator compared to simulations and see how. But it could be, I don't know. We'll see. Eventually we'll compare with them. Okay, so to finish, I want to. So we see here very reasonable agreement between the calculation and the simulations. Now I want to get this into a more practical application. If we want to put a number on how much nonlinearities affect the measurement of acoustic scale that will be done in galaxy surveys. So as I said, from the correlation function perspective, the traveling feature is that this mode coupling generates a shift of the acoustic scale, and that can bias your determination of cosmology, for example, the dark energy equation of state. From the power spectrum, it's a little bit more tricky. And so let me explain exactly how this. So from the correlation function, it's simpler to see, but because people now are using the power spectrum and they say the power spectrum somehow is not affected like the correlation function, which I don't think is true. I want to use the same method that people have recently used in 2D and Sloan to measure this. So the way people do this in at least as of 2007 is to you measure your power spectrum with acoustic oscillations in a galaxy survey, and then you define a smooth spectrum, which essentially goes in between the oscillations, right? Which is, roughly speaking, will be the power spectrum that you will get if there were no baryons in the universe. Okay, it will be some smooth quantity. So I'm going to define that by just because for that smooth initial condition, you will still have this relationship where now I will have smooth mode coupling and smooth initial conditions times a propagator. This propagator is exponential. It's a Gaussian. It's a smooth already, so it's the same, essentially the same thing. So if I do the ratio of the power spectrum wiggles to the smooth one, which you can define, so people observationally they define by just putting some nodes and averaging out the wiggles, and they do a spline fit, and that's how they define it in the observations. So that ratio of power to smooth power is denoted as B, and you can write it down as two terms, one which is proportional to the wiggly initial power to the non-wiggly initial power. So this is the unperturbed acoustic oscillations, which get modified by this function here, which is just a propagator essentially. Okay, so this gets dumped again, plus a term that depends on the ratio of the mode coupling for wiggly divided by no wiggly initial conditions. Okay, so what people have assumed in this paper, they assume that this extra power mode coupling, because it's generated at small scales, it has no information on the baryon acoustic oscillation. So they say, okay, this is essentially the same as this. So this is 1. Okay, so if this is 1, right, if you look at the nodes of oscillations, which is where this ratio is equal to 1, when this is equal to 1, if this is 1, then this guy is also equal to 1, because you got G plus 1 minus G. And so these nodes will be unperturbed. And so they say, no matter what nonlinearities there are here, if they are smooth, then you will get the same answer in the nonlinear case and in the linear case if you do this kind of method. So however, this is not quite true. So let me now show what happened. So these are the initial, so this B0 is the initial power spectrum with wiggles divided by no wiggles. Okay? So this is something that oscillates about unity. Okay? And the nodes of oscillations are denoted by these scales here, okay, where the linear wiggles cross 1. Okay? So these are these scales. So these are the scales that they are using to determine the sound horizon. And if you look at the mode coupling ratio, you see that actually this is not smooth. It's not equal to 1. It actually has oscillations which are 90 degrees out of phase compared to the original acoustic oscillations. Okay? And this is actually very easy to understand. Essentially what's going on is that if you have a power spectrum that, let me exaggerate, okay, these are big wiggles, and then you start with something which is smooth. Okay? So B0 is the ratio of this to that. Okay? So here is above 1, then it's below 1, above 1, below 1, and so on. So people want to use these scales to measure dark energy or cosmology. Okay? But now what happens is that the nonlinearities actually depend on the local spectral index, okay? Meaning the slope of the power spectrum. So here I'm plotting P as a function of K. Okay? So what the acoustic oscillations do is this is a smooth spectral index, right? It's becoming more and more negative. The derivative is becoming more and more negative as you go to higher K. But it's relatively smooth. Okay? So what acoustic oscillations do is they modulate the spectral index. So here, for example, the spectral index at this point is much more negative than in the smooth case. Okay? So when you have a more negative spectral index, essentially you have more power at large scales compared to small scales, so things can collapse more efficiently. So actually, here, structure grows a little bit faster than compared to a smooth model. Whereas when you go in this side, the spectral index is more positive than for a smooth thing. So actually, the power spectrum grows a little bit slower. Okay? So as you can see, if I add a positive thing at this particular scale, and then I add a negative thing here, I will cause a shift, because essentially it will do something like that. Right? So the growth, when I calculate the nonlinearity, it will be higher here than for a smooth, and here it will be lower. So that's where this 90 degrees out of phase correction is coming from. So here, when the derivative is maximally positive, you grow less. When the derivative is maximally negative, you grow more, and then you grow less, and then you grow more. And so here you subtract. If you subtract, you move this down. Here you add, so you add it down. So that where it crosses unity actually shifts towards smaller scales. And you can calculate how much it shifts due to this effect as a function of redshift for all the nodes. So the first node, the second node, the third node, the fourth node, and so on. And you can also calculate how much the correlation function peak shifts, and they are of similar order. Okay? And so notice that, say, for redshift half or whatever, so the effects are of order 0.4%. So if you multiply that by 5, that gives you a systematic error on W of 2%, which is something that we hope we can do. And in fact, I should stress also that this calculation assumes dark matter is for dark matter in real space. In reality, you are observing things in redshift space, which enhances this effect, particularly a high redshift, where omega matter goes to 1. And also, if you have biased galaxies, because they tend to they are in high density regions where the collapse is stronger, it also enhances this. So you should multiply probably by a factor of higher than 1, like a factor of 2 or something. So something to worry about. Okay, so I'm out of time. So you can ask me about this if you want later. So let me conclude. So this renormalized perturbation theory gives a well-behaved approach that is not limited to the amplitude of fluctuations. The power spectrum is in good agreement with simulations. We have, I can mention this a little bit if you want. We have extended this to higher order statistics, and it's looking good. We can calculate how the acoustic peaks shift, and they are of order 1% or so, and this is relevant for observations. The good thing is we can understand how these nonlinearities work from kind of first principles, and we can include dependence on cosmology and things like that. And I should stress, as I said before, these nonlinear effects occur at very large scales and are not related to visualization of halo profiles, which otherwise will be very hard to include. This is something that happens at much, much lower densities than visualization densities. All right, thanks.
So basically, this RPT method allows you to evolve power spectrum, right, into the nonlinear. So one problem other than baryonic oscillations would be to see how. So if you start with power spectrum which has a truncation at high base, how would this truncation scale evolve with time? So that would be relevant for the problem of caustics.
Right.
So how small caustic structures become with low, like as you go in time.
Build only for high redshifts.
Yeah, the problem with caustics is that you have to include shell crossing, which is difficult to include. So we are starting to do that.
But your RPT is exact. So
No, it's not exact because it assumes we are working in the fluid approximation. So we are solving 3 equations, out of which 2 are exact. So we are 2/3 exact. Okay, that's so-called Italian mathematics. So the momentum equation gets modified because once you get shell crossing, you build a stress tensor, which we are not including. And so we are starting to study that and see how important this is at small scales. What?
All dynamics is different from all streams.
Yeah, but there is I don't think it's as bad for Eulerian perturbation theory as for Lagrangian. So in Lagrangian it's really bad because you're expanding about trajectories. So trajectories cross and they don't see each other. And so something that should virialize once the trajectories cross, they should virialize and stay there. In Lagrangian perturbation theory, just keep going. And something that should be a high-density region converts into a low-density region. Whereas what you are doing in the Eulerian case, you are averaging over, you define your velocity field by some average over the Blasov. So you have to solve the Blasov equation and integrate over momentum. That's your velocity field. Okay? So if you have a region where you have 2 streams coming in, right? What Eulerian perturbation theory says is that essentially because you have this and this, essentially if they are against each other, it replaces this by 0 velocity field, which is much more accurate than saying the trajectories cross and it converts into a low density region. So this will be, in the simulation, you will see shell crossing, you will see something like this, oscillate, and then they create a halo. In Eulerian perturbation theory, once they cross, essentially it remains a small velocity. And so it actually gives the opposite effect. You tend to overestimate the power. So it's a different... Well, 3 streams there is more complicated because there could be... Yeah, if you have multiple streams. But essentially you are replacing this by the center of mass velocity of the thing. So it's a better approximation, but still, it's not correct.
The question is, what else can you do with this heavy-duty method besides? You also do the acoustic oscillation problem.
Right. Well, you will have, if you can include these effects, you can hope to go to smaller scales. But so far,
There's all kinds of other things other than acoustic oscillations that are sensitive to the same.
yeah.
Like neutrino mass is the same.
Yeah, you can, anything that is at large scales, you can,
So you can do the smallest
yeah, right.
Any linear to weakly nonlinear cosmology.
Right. Yeah, also you can extend this.
It's all in D+. All cosmology is in your.
Okay, not quite.
Where else?
So actually, one of the extensions that we are doing is like once you are nonlinear, the decaying modes are important. And the decaying modes are not exactly related. Like I was assuming that it was D+ to the -3/2. And that's not quite true. So you have to include that effect also. And so there are other cosmological dependencies that come in, which that's very easy to include. It's just, we just did the easiest thing. But It's not just D plus.
You want to tell us about extensions to higher order statistics?
Right. So if you want to calculate higher order statistics, then say the 3-point function, right, or the bispectrum, you have to calculate things like this. So remember when I said when you calculate the 2-point function, then essentially you have a term here, which is g squared times the initial one plus p mod coupling, okay? And this guy is just the cross correlation between g is proportional to the cross correlation between initial and final conditions. So when you do the 3-point function, you get similar quantities, which now are essentially cross correlations like this, and so on. Okay, higher order cross correlations. And the question is whether you can do the resummation the same way. So we have this paper with Francis Bernardo and Martin Croce showing that you can actually extend these resummation techniques to all higher order to arbitrary high order correlators. And this is an example where we so once you are in 3-point function, then you have 3 Ks, you have a triangle, so you have to talk about what configuration you're looking at. So this is for equilateral configurations of redshift 0. And this is this quantity now that is the equivalent of G for higher order functions, now divided by D squared. And so 3 level will be a constant here. And so this is the one loop perturbation theory, goes like that. And again, it goes negative to minus infinity, whereas the right answer should decay to 0. And this is the answer in the Heikel limit. And it works very well with. Also, if you do different configurations, this is for a configuration where the triangle is not equilateral, but it's like collapse along a line. So you get a similar good agreement. So it seems to be doing well.
So is modified gravity, straightforward to sort of here, or?
Yeah, I'm thinking about that. It depends. So you have to do it case by case. But I'm looking at the so-called DGP gravity, which has other signatures. So there are many nonlinear effects in that theory. So for those of you who are not familiar with it, this is a modification of gravity where gravity becomes 5-dimensional at large scale, so it becomes weaker. And it explains the acceleration of the universe without a cosmological constant or a dark energy fluid. So it's just a modification of GR at very, very large scales. And in this theory, what happens is that at weakly nonlinear scales, you have an extra scalar degree of freedom. And this extra scalar is essentially, we live in a brane, okay, which is our 3+1 universe, and there is an extra dimension which is perpendicular to it. This extra degree of freedom is essentially the bending of the brane. So it's called the brane bending mode. So if you have a brane and you put a source, right, this brane bends due to gravitation. And this extra scalar degree of freedom modifies gravity. And that's how you explain the acceleration of the universe. So however, so the Poisson equation gets modified. And it gets modified into a nonlinear quadratic equation. So there are extra nonlinearities in this theory. And so there are many things you have to worry about. Some people use like baryon acoustic oscillations to rule this theory out. But in this theory, there are extra nonlinear effects that in principle can shift the acoustic scale if this theory were correct. So when trying to rule this theory out with baryon acoustic oscillations, you should include this. And so there are nonlinearities which actually work in a funny way, because this extra scalar degree of freedom, if survive at small scales, it will be ruled out by solar system tests. So this extra scalar degree, at small scales, you should recover general relativity. So you should kill this scalar degree of freedom. And the way the theory does it is very clever. It's by these nonlinear effects which actually kill this extra degree of freedom. So it's a nonlinearity that actually kills something instead of becoming dominant at small scales. So I've been actually trying to incorporate that into this kind of framework. And it's actually not very hard. It turns out that these vertices that where the interactions happen now are a bit modified. But it looks like similar ideas can be carried out there as well.
Don't you apply the superposition principle in order to actually that you can combine Because you don't have any more small position parameter than this series, right? Because it's non-linear.
Right. So I'm not actually. So the I mean, since this normal gravity is already okay, it's linear in the field equation, but it's non-linear in the other two equations that you are solving. Okay, so you are when you calculate quadratic corrections, you are including these non-superpositional things. So now you have to worry about no superposition in the potential with respect to density, which you can do. It's just another source of interactions. So it's a bit more complicated, but it's not. The same ideas can be extended.
The matrix you had will be not 2 by 2, but 3 by 3 by.
Right. Exactly.